a day of simulation of clouds. It's a very high-resolution cloud model, 3.5 kilometers per grid cell, written out every 10 minutes, and you can see just how complex the cloud field is over the Earth. The clouds are moving. You've got very small clouds that are moving. You've got big systems that are moving, and then you've got areas that are cloud-free. You know, from your experience looking at the sky, how the clouds can change. But this is showing now that as we enhance our computational capability in the physics-based sense and observationally informed, we're beginning to be able to look at in clouds and better simulate the variability of that. Again, to have a lot of these features. And it's they're color-coded for different kinds of aerosols. So blue will be sea salt, red will be, I think yellow is mineral desert dust. You've got green for carbon aerosols and biomass burning, and white is for sulfate. It helps one remember that when one's looking at atmospheric aerosols, it's a very complex situation because, you know, for other things, when we show you trace constituent maps like for ozone or nitrogen dioxide or carbon monoxide, you know, one molecule is essentially the same as any other. But when you're looking at aerosols, that's not true at all. So you can see, dust is red, sea salt is blue, organic black carbon is green, and sulfates are white. So depending on what part of the world you're looking at, you see very different things. You see the sulfate aerosols in the southern hemisphere. You see green things coming from biomass burning, coming westward off of the coast of Africa. You see mineral desert dust, and you can see that it's working its way all the way over the, some cases, the northeast coast of South America, over the Caribbean, and then the white sulfate aerosols. You see a lot coming from areas where there's a lot of fossil fuel combustion in East Asia, South Asia, Central Europe, and the United States. These aerosols have important climatic effects. They have, at nose level, they can have important human health effects because they contribute to particulate loading, PM 2.5, PM 10, and sort of if you're in an otherwise pristine area, they can create atmospheric visibility effects. So the aerosols, and depending on what the aerosol is, it can either be warming or cooling. The sea salt aerosols tend to be reflective, so they can be cooling, but some of the other, especially the carbon ones, absorb radiation and they're warming. And the understanding that we have of aerosols this represents an enormous change probably over the last 20 years or so. I think if you go back 20 years, there were no global pictures like this of aerosols, and there were no models that are capable of simulating the distributions. So this becomes important for people who are really trying to understand aerosol impacts on climate, because that's still one of the big unknowns in terms of forcing in climate models is how do aerosols affect the properties of clouds. We now have some satellite data, for instance, that show that areas where the clouds are affected by aerosols have different properties in terms of optical properties, particle size distribution, and even precipitation formation potential than clouds in areas that are not affected by aerosols. So our ability to address that kind of science is something that represents a great advance over the last 2 decades. But through some of the radar observations, space-based radar or airborne radar, one can actually see that ice does flow. And you can actually get a sense as to where it's flowing faster than others, and begin to understand what the implications of that may be, because if the ice is flowing out, especially if it starts melting at the edges, which it has been, then the ice can get transported from inland to the sea, and it provides a faster way of melting ice if you have that faster flow. Next is going to go down to the opposite end of the world, and this is Antarctica, and do a similar kind of thing that'll show some of the ice flows in Antarctica. Again, one can sort of see the drainage patterns and see that there are a number of areas where the ice definitely flows and is flowing in from a long distance away, and then there are some other areas where sort of the flows are narrower and not covering as much distance. So again, the radar measurements have been very important in being able to do that, because otherwise I really don't know how else you want to do that. Next is a very different kind. I'm sort of going from cold to hot, because that was ice. This is lightning, and this is a lightning climatology over the course of the year, and you can get a sense of where the thunderstorms are. And again, this comes from a couple of different satellites that took place over a number of years, and you can get a sense. The black is very high, the sort of the pink and red is pretty high, and then by the time you get down to the blues and greens and even yellows, it's not that much. So there's a number of things that you can see as part of the seasonal cycle here. You sort of have to look at it multiple times. You can see the highest amounts of lightning are in tropical regions, especially South America, Central America, Africa, Southeast Asia, Indonesia. You see some up here in India. You can see a very large seasonal cycle as you get into the northern hemisphere. You get into the summer months, it's much higher. Administration has it. It doesn't show those of our international partners, especially in Europe, Japan, China, Russia, India. You can see lots and lots of abbreviations. There's a few things to point out. You see most of them are going over pole to pole because they're in what we call polar orbits. It means that they cross over the North Pole and the South Pole, typically about 15 times a day each, in this low Earth orbit, which is typically 700 to 900 kilometers up. The satellites are moving at about 7 kilometers a second, and that means that 14 to 16 times a day they go around the Earth. They go from the bright side of the Earth with the full sun on them, and then almost instantaneously they're on the dark side where it's really cold, and then about 45 minutes later they'll come around on the bright side, and the sun will be shining on them. So it's a great engineering achievement. The opposite side of the world, this is the Antarctic, and it's going to converge in on the Pine Island Glacier, and then the technique of trying to look at ice velocity, which normally comes from radar measurements, but then if one looks or compares different years, one can see that there's an increase in the ice velocity. And again, this is the sort of thing, it's very hard to imagine without, there's an elevation change, and you can see a drop. That without the sort of the repeated viewing that you can get from space, or some similar remote sensing methods that can be done by airborne observations, it's very hard to imagine how you would get this degree of coverage to spend that much time in very high latitude regions where it's just hard to work. Next is this is a global view of temperature. It's 5-year averages. So for now, this is based, go back into the early part of the 20th century. It's based on surface measurement data, and this represents anomalies. So you don't see sort of the normal temperature scale because they're subtracting off the means. But as you see over time, you're going to see a lot more yellows than you saw in the past, and you're getting to reds that you never had. And you can see the reddest of the red tend to be at high northern latitudes. So that it cycles back. So again, you can see that from the point of view of temperature change, when you're looking at that there really is a change, and you can see that the geographical patterns, that in some cases continental areas are warming more, but especially the fact that the largest warming takes place at high latitudes, which are very sensitive, because that gives you increasing temperatures at high latitudes, increases the possibility for melting ice. You have a measuring mission that lets you essentially look inside hurricanes. So people talk about doing CAT scans or tomography of hurricanes, getting information about the vertical distribution of rain, look at the eye walls of hurricanes. In some sense, you can kind of get, really it's like, think about what it would look like to go in the middle of the hurricane, in the middle of the atmosphere, look down and look up and see where the precipitation was. It's a great way for meteorologists to learn how hurricanes work, to build their models and to test their models, because as we've seen that extreme events are very, very important things, and increasingly important as we come to expect that the nature of those events may change in the future. So really having a good sort of quantitative, physical, mechanistic understanding of how these systems work will enable us to have improved predictive capability for the future. All right, this year is the biggest year in a long time for hurricanes. We had so many hurricanes that we actually ran out of letters in the English alphabet for naming them, and had to sort of went to alpha and beta. So this shows the model simulating storms, and so this, because it's a model that was run forward sense for a number of months, it doesn't show the actual storms like Katrina and Rita and Wilma. As I said, 2005 was a really good year for destructive storms, but it gives you the sense, because of especially very high heat loading in the western Atlantic Ocean and Caribbean Sea and the Gulf of Mexico, why it became such a big year for hurricanes, and not just the number of hurricanes, but for the destructiveness of the hurricanes. And it's giving some sense of our ability to start doing the kinds of seasonal forecasting and other things. And again, this kind of forecasting is not to forecast specific tracks of storms months out, but it gives you a sense of the fact that one could look at the, get a sense of how bad a hurricane season is going to be. So that's what I'm going to talk about now. I stick